Similar to black holes, sounds also kind of easy. Giving a little bit more details. So I was born in Upper Austria in Linz, which is a Sabato kind of country. You all know probably Germany, which is just south of Germany, and my hometown was Linz here in Upper Austria. The famous two cities maybe in Austria is Vienna, the capital, and if you have known or heard of Mozart, he was born in Salzburgo. If you like the mountains and skiing, you should go to this area, Innsbruck. So I was born in Linz. I visited a technical college there. So I have a high school degree in electronics telecommunications. And after doing my high school degree and the mandatory military service, I moved to Graz, which is in Austria, to give you, because I guess as Colombians, you don't know Graz very well, or Austria, maybe also not Europe too well. So Graz is the second largest city in Austria, and it has a population a little bit below 300,000 people. So minor city for you guys. And Linz has about 200,000 people. So we are a small country. If you're interested in astrophysics, in Austria, we have three places. So one is, of course, in Vienna. There's an Institute of Astronomy. I think they're specialized in stars, so more stellar. And they have an observatory somewhere here in Lower Austria. Then there's an astrophysics group in Innsbruck. They are specialized on cosmology and astroparticles. I think they also offer an international master degree in collaboration with two other universities. So if you're interested in cosmology, astroparticles, this might be a place to go. And then there's a third group, small group, as I said, to which I belong, which is in Graz, and we are doing solar stuff. We have a small observatory in the city and a second observatory here in Carinthia, which is a very nice state with mountains and lakes. And this is our solar observatory here next to a lake. These are some impressions. So this is the main building of the university where I studied most of the time, the Karl Franzens University. So it is this imperial, how should I say, construction style. And this is the main building of the technical university. So as you can read, I studied at two universities. I did a master degree in physics and later with specialization in astrophysics and solar physics on the Karl Franzens University. And I thought, okay, astronomy, if it doesn't work out with science, you should go to industry, but then astronomy is probably not the best study. So in parallel, I did a second physics degree, a master degree at the Technical University in Graz. So I have double master degree in physics. And after the physics degree, I continued with a PhD or doctoral study at the Karl Franzens University in solar physics. This is the observatory, as I mentioned, down here. And this is our patrolling observing telescope, which does full disk observations of the sun, the so-called Kanzelhöhe Observatory. Now I want to convince you that this was wrong, what was in the beginning, that the sun is boring and there's nothing to do and nothing to see. So, of course, stories start back with Chinese astronomers thousands of years ago observing first sunspots. But actually, a step forward was with Schwabe, German astronomer in 1840 around, who realized he was very interested in the sun, and he practically went out to observe the sky every day when he could, when there were no clouds, and he did that for years and years. And after gathering data for 10 years, he started to realize that the number of sunspots, which is plotted actually down here, is changing over the time. And he realized that there's kind of 11-year cycle in the number of sunspots on the sun. It was, of course, totally unknown what are sunspots and are they interesting or not. But he started to realize, okay, this number is variable, it's changing. And this gives rise nowadays to the famous sunspot diagram and butterfly diagram. So if you just plot the number of sunspots, you realize you have an 11-year cycle, and this cycle is variable. So the number of sunspots increases, decreases, and so on over 11 years. If you also plot the position where you find the sunspot on the sun, then you see that in the beginning of a cycle, like for example here in 1880, the sunspots are far away from the equator region. So this is the equator, this is north of the equator and south. So the color gives you how many sunspots are found. So yellowish is more sunspots, reddish less, and then of course the position. And this looks like butterflies, that's why it got the name butterfly diagram. And you see that these sunspots start to migrate during the cycle closer to the equator, and that there are stronger cycles like these one and weaker cycles. A major step forward was then, a first step forward was actually just like 20 years later. It was the so-called Carrington event. So there was another astronomer, Carrington in Great Britain. He observed the sun, and while looking at a sunspot, suddenly he saw huge brightenings happening. So probably, as we see, he did a drawing of what he saw on the sun. This is the sunspot, and he saw this bright stuff happening there. This is what we probably nowadays would call a tooth ribbon flare. So this brightening is caused by flare, a magnetic huge explosion on the sun. And actually, when fast electrons hit the surface of the sun, they can heat up the surface and it becomes bright. And this is called a white light flare. It's very rare and it's very active for our space weather. And the funny thing was, what he realized is a few days later, there was a geomagnetic event. So these people in the 1800s, they were interested in the magnetic field of the Earth because they needed it for shipping, to navigate around the oceans, especially the British. And so these British people had set up several geomagnetic observatories, among them one in India. And this geomagnetic observatory, a few days after these observations of Carrington, the geomagnetic observatory got crazy. Like the magnetic needle pointed in all kinds of directions, and the magnetic field of the Earth was super disturbed. And it goes back to Carrington to realize that what he saw on the sun, this sudden brightening in the sunspot, is correlated with this geomagnetic storm on the Earth. And this is kind of founding and starting the age of space weather, the interest in what's happening on the sun, how is it influencing the space around the Earth, and what can we learn from it. And a major step forward, because still we didn't know what are sunspots. They're just dark areas on the sun. Let me see if it switches, at least, yes. Major step forward was in the early 20th century, around 1910. So George Ellery Hale, I think, from the US, he realized when he put a slit spectrograph across a sunspot that the line, the spectral line he observes, starts to split up in several sublines. So obviously, lines are formed by the energetic transition in the atoms when the electron jumps in the orbits of the atom and it emits the photon. So under the influence of the magnetic field, this was a Dutch scientist, Zeeman, and now it's called the Zeeman effect, that the energetic levels in the atom starts to split, and you see several transitions. And George Ellery Hale was aware of the research of Zeeman, which published a year, 2 years before, and he figured out, okay, if I see these lines splitting over the sunspot, then the sunspot is magnetic. So the sunspot is caused by strong magnetic fields. So you see how the knowledge evolves. And nowadays, kind of lately, only due to the advent of the space age, we have access to other wavelength bands, not only the visible light or the radio, but we can also go to X-rays and ultraviolet radiation and so on. And we see here an image from the from the Yokohama mission, I think. It's probably written, yes, Yokohama mission from the Japanese one. They had an X-ray telescope on the sun, and then they observed the sun for 11 years. So for the whole cycle, which is depicted with the sunspots, you can see that the outer atmospheric layer, the so-called corona, is highly variable. So in a solar minimum, where you don't see any sunspots, the corona becomes kind of dark. While during the maximum, when you have all these magnetic sunspots on the surface, the corona becomes highly active, heated, and very bright. So a clear indication now, which we have, and spanning from the 1840s till the 1970s, that the sunspot activity, which is magnetic due to George Ellery Hale, causes huge changes in the solar corona, in the outer atmospheric layer, which is then influencing our space weather and the space conditions around Earth, which is of importance for manned space flight and also, of course, for satellites, telecommunications, and so on. So I strongly disagree with the idea that the sun is a little bit boring star. So actually, it's kind of really, really interesting. But I'm not so much interested in the large scale stuff as we saw before the sunspots. But if you go to the sun, you see that you have magnetic fields not only on the larger scales. So sunspots have diameters of the whole Earth, but it goes down over magnetic bores, which are maybe 1,000 kilometers wide in size, to magnetic knots and flux fibers and single isolated magnetic fields and flux tubes. And this is more the range where I'm interested in and what I'm studying. And these single flux fibers can be often seen as so-called magnetic bright points. And this is practically my research field since I finished my master degree. And they were known or are described since the 1970s description. So in this early paper from the 70s, people described this very small scale, and small scale on the sun means still a few 100 kilometers in diameter, magnetic fields as being aligned around these granules. Granules, which we see here in the modern observations, are these plasma bubbles of hot plasma rising to the surface of the sun, where it cools down and it goes down again in these intergranular lanes to the border of the granules. You can imagine granules always just if you put a pot filled with water on the stove and you heat up the water, you see the convective circulation starting in the water with hot water rising up and then sinking and forming up this cellular pattern. The same happens on the sun, and these small scale magnetic fields, they are swept into these intergranular lanes where the plasma stream is flowing down actually again, and it's concentrating the magnetic fields, and then it's forming these so-called magnetic bright points. And I'm studying these. So we have here different observations. This is from the 80s. You see the quality compared to modern observations is kind of low, even though these were superb observations back then. Little bit more background to these magnetic bright points. So they are small scale features and magnetic. What does this mean? Magnetic in our case means that the fields go up to the kilogauss regime. So a sunspot has a few kilogauss. These magnetic bright points normally something like 1.2 kilogauss. They are small. Small on the sun means they are at the resolution limit. So the smallest sizes we can currently see on the sun, and that's still in the range of a few 100 kilometers. So bright points probably at the moment they go from 30, 40 kilometers. So this is probably the size of all Bogota up to 200 kilometers, which is more or less half the size of Austria. So this is kind of what we can see and resolve on small details on the sun. They are especially bright, so they are brighter than the surrounding what we saw, and we discussed it already. They are found between the granules in the so-called intergranular regions, and they live for several minutes. So this is very short time scales on the sun. If you think of sunspots, they can survive for days, even weeks. So if you have a huge sunspot group, they might survive for several solar rotations, and the solar rotation is like 5 days. So these guys are really fast in their evolution. You can describe them in a theoretical model, in an easy model by so-called single flux tubes. You can imagine that all the magnetic field, which is in the bright point, is concentrated just in one strong vertical field. And this vertical field starts to expand in size when you go higher in the atmosphere, as the gas pressure is reducing outside. So it becomes broader and broader, till at some point in the solar atmosphere, all these neighboring flux tubes start to merge. So they form like a carpet layer, they merge together. Depending on the magnetic field lines, if they're closed with some neighboring magnetic fields, you can form some small loops in the atmosphere. Or if they are open, you can get an open field line configuration where you can get then the solar wind. So particles streaming away from the sun into the space, creating the wind, which we can also measure at Earth. And there's a theoretical concept how you can create them. That's called the convective collapse process. And the whole idea there is just when you press the magnetic field together and it builds a strong enough magnetic field, at some point you can suppress the convective motion. So normally energy is transported from inside the sun to the outside via these convective cells, so the hot plasma which is rising. And when the magnetic field becomes strong enough, it can suppress this convection motion, so you get no new energy into this magnetic field configuration, but still the photons and the radiation is escaping. So what happens is that the plasma inside is starting to cool down, it becomes dense, denser plasma is heavier, it will flow down along the field lines and start to evacuate locally these flux. So the evacuated flux will collapse, shrink in size, and become very strong. And this process is called convective collapse, and it was described in the 70s and then observed in the 2000s now and confirmed. And what I started with was that my supervisor back then was interested in these features, and he told me during my master thesis, go and analyze these bright point stuff. So what you need to do is then you need somehow to segment them out from the image. So if we see here an image from the photosphere with a magnetic core, so strong, larger magnetic field, which is between the sunspots and the bright points, we see the granules here, and we see here the bright points. You somehow need to get the information about them. So what you need to do is a segmentation of the image. So this was my first task, kind of in the master thesis, to write an algorithm to segment the image, to get the information of the bright points, to analyze them. And how could you segment an image? My idea was, if these are all just intensities, if you think of the intensities like a landscape, then these granules, they would form like mountains, but like mesa mountains. So flat mountains. So you have the intergranular lanes, these are the valleys where the intensity rises up, then on the granule, it becomes flat, goes along, and then falls in the next intergranular lane. And the bright points would be like very spiky small mountains. So what you could do is you go to your landscape, to the intensity image, and you threshold it from the top to the bottom. When you do this, the structures will start to grow. This is shown in this video. I hope it plays, and the transmission quality is not too bad. Well, maybe with the internet it cannot play it, so videos are maybe here not so good. What we should see is when we lower these thresholds and we go through the image, then you see always new pixels coming up to the structures you already have. Ooh, so no more videos, I guess. I'm sorry, it's starting, so it should be back very soonish. Presentation is coming up again. Sorry for this. Let's share the screen again. Screen sharing on. Presentation from the beginning. Or we skip the first slides. Go somewhere here. And then, oops. Then we hope that it doesn't crash again with the movie. I don't try to play it. As I said, you should see the segmentation. And then the next point is, sorry? Okay, I will just continue with this technical stuff. I don't care too much if it interrupts. So what we see here is after the identification, we see two different images. One is a G-band, so this is practically the visible surface of the sun, and all the crosses mark now identified bright points. So we see a sunspot, some wrong identifications inside the sunspot, and the bright points identified outside. This is a magnetogram. Magnetograms show you just the magnetic field, more or less the vertical magnetic field, so where magnetic field is coming out from the surface of the sun or going in. And the two directions of the field lines are shown in black color for the one field and in white color for the other. So one means positive coming out, the other negative coming in. So this shows you that practically this identification works and identifies regions of strong magnetic field. But what you want to do is then, you not only want to have static parameters, you want to track the feature. So you want to follow the feature, how it moves, how it dynamically behaves over the time. Then you can study the temporal evolution of these bright points. And this is not so easy because these bright points, they merge and form one bigger bright point. Sometimes they like to split. So one bright point, which is big, it splits up into two, and then two of them go along. So it's kind of involved to think about how you create the tracks, the correct ones, to say what is a bright point and to follow it in the time evolution. So my easy solution in the beginning was just go for isolated bright points, which don't do splittings, don't do mergings, then you have no problems of tracking. And that was enough practically for getting my master's degree, which was then something like November 2007. So I started with the master thesis in autumn 2006. So after a year, I got my title, and I was allowed to go to a first national meeting with this poster. For doing the poster, I earned myself 50 euros. I was very happy as a student. You some money, we can have some party. This was a group picture actually in this astronomical institute in Vienna. It's very nice old building. They have a huge telescope, I think probably one of the largest refractors. And these cupolas, the domes, they are connected to this institute building. So if you go down this corridor here after this door for a few rooms, then you end up in a huge cupola dome with one of the largest refractors, I think, in the world from like beginning of the 20th century. And this was our group, and I think this is the guy which I was back then, so more than a decade ago. And as the master thesis went so well with the first kind of ugly looking poster, I thought, okay, let's continue and do a PhD on these bright points. But why should one do bright point research? Why is this interesting? So maybe we should talk a little bit about science questions, because now we know, okay, we can observe these, we can segment them, we can identify them, but what are the questions they are involved in? So one of the cornerstone problems in solar physics is actually the heating of the upper layers of the atmosphere. So if you look at the visible surface at the photospheric level, then we have a few thousand kelvins. So generally 5,700. In the sunspots, the temperature is lower. That's why they are dark, maybe 4,000 Kelvin. But when you go further up in the atmosphere, first the temperature decreases, which is natural for most bodies. When you go away from the source of heat, it's becoming cooler and cooler, but not so in the sun. At some point, you reach a temperature minimum, and then slowly the temperature rises again. That's called the chromosphere, up maybe to 10,000 Kelvin. So we have already doubled the temperature than on the surface. And then when you go further, you end up in the transition region, and then suddenly you're in the corona, which is absolutely non-dense layer. So there's nearly no atoms left. But these few atoms which are left, they have temperatures beyond the million Kelvin. So they have million, 2 million, 3 million Kelvin. And this is the cornerstone problem of solar physics. How can you get so hot outer layers? How can you manage to increase the 10 degrees 1,000 kilometers further away from the sun? This is counterintuitive because normally everything gets cooler. And two possible scenarios which are followed up in science up to these days are wave heating processes. So you create some waves like sound waves, MHD waves in the surface or on the surface of the sun. These waves travel upwards to the corona, then they get absorbed there, and while being absorbed, they heat up locally the surrounding. The other generation process for energy people came up is reconnection heating. So we talked before that the magnetic fields is the most interesting stuff on the sun because it makes the sun dynamic. It creates all kinds of activity and phenomena and plasma physics, which is interesting to study. But one of the interesting things is this reconnection. Reconnection means, I think I have even a picture. Yes, I'm sorry. These were the pictures for the wave heating because we have magnetic fields and we have these flux tubes, as I said before. And these are three typical waves which you can create in the flux tubes. One is sausage modes, and that's more or less when you take your toothpaste and you squeeze it, and you have locations where you squeeze the flux tube, seen here, locations where it's broader and squeezed again. And that's why it's called like a sausage mode. Then you have the transverse mode, kink mode. This is when you have the flux tube and you just do a rapid kick to a side, then you create the kink, which is traveling up. And the third one is torsional. This means when you twist your flux tube. And these are waves which can propagate upwards and being absorbed and heat the atmosphere. And this is the sketch for the reconnection heating. If we have two magnetic fields of opposite directions, so one line is coming here from the right going to the left, and here on the south, we see a line coming from the left and going to the right side. If you start to bring them together through some process, which we don't go into the details now, then at some point you form this reconnection zone. So when you bring the magnetic fields close enough together, you create lots of current density, because one of the electrodynamic laws says that the rotation of the B field, so how much magnetic field is an area and how much it changes direction, creates practically current. Plasma is not ionized enough, you start to dissipate energy. So energy is lost via the currents, and the magnetic field lines start to break up, reconnect to a newly topology, which is shown here. So practically the field line which was going before from left to right, is now going from the left to the left again. So you form these kind of loop structures. And that's magnetic reconnection, reconnecting two opposite polarity fields. And in the process, in the zone where you reconnect them, lots of energy is set free and can locally heat the plasma. Other interesting questions, of course, is we know the global dynamo shown before with the variable solar cycle and sunspot cycle, which has 11 years. Sunspots are due to the magnetic field. But the question is there a local dynamo? Is there a second dynamo acting just on the surface and creating the small scale magnetic fields? Then you can ask, how are these magnetic fields on small scales transported, amplified? Is the magnetic field coming from decaying active regions or from the local dynamo? How is the magnetic field coming to the surface, which is called flux emergence, and so on. So now we know that probably these points are interesting. So what happened in my career was that in 2009, I went to a first summer school. It was a dedicated summer school to solar magnetism. And I can only strongly encourage, well, this is for me not the most important stuff, but the most important stuff for me is the networking. So this was the group of people, the students, with some professors here shown, and lots of these students of my colleagues, they are still active nowadays, and I'm still in touch with them, and we have them like working corporations nowadays. So it's very good not only to learn about your field, but to build up actions you need in the future. So he is a Czech colleague, and we have some working collaborations with colleague. This is a Hungarian colleague from Concoli Observatory in Budapest, and there are many more colleagues. So this was later a colleague of mine when I went to Spain, we will see, and he's now working in the US at the Malat Space Science Laboratory, and there are a few more colleagues, like Slovakian colleague, Italian one who are still active. And also you can start to fall in love or have some relationships if you are interested in some people, but they might not work out, which we will see also later. And I'm more on the funny side. So as I said, we partied a lot. We have these kind of conferences, summer schools. You can see interesting, big science experiment stuff. So in our case, in the Netherlands back then, they just built LOFA, which is low frequency array. It's a radio telescope consisting of tons of these kind of small antennas in the low radio frequency bands. And so on one excursion day, they carried us there. Back then, I didn't appreciate it too much because practically we were sitting 2 hours in a bus to be driven to a former swampy area, and then there is nothing because they dried up the swampy area, and they put just till the horizon, more or less, these small 1 meter kind of lambda quarter antennas. So it was a very hot day. I'm kind of sleepy, and then this is the big thing they show you, an empty field with just sticks coming up. But at the end, I mean, LOFA is interesting, but what we saw there was not too interesting for me. Time to continue with some science going back. So my first paper was then about the size of MVBs. So if you segment the images, you get the bright points, you identify them, you can do a size distribution. And actually, I worked with the satellite data, which we will come to later. And I realized they deliver two kinds of data sets, like fully resolved data, which are plotted here. So the histogram gives you the measured size distribution of these bright points, which were around 160 kilometers. And the full line is a line fit plotted through it. But they have also reduced data sets where they do an onboard binning, where they count together 4 pixels to reduce the amount of data which they need to transfer. So just the pixel size is bigger. But with this data set, with increased pixel size, the size distribution shifted. So the question is, physically, nothing happened. The bright point is the same. So why should the size distribution change when you change your pixel sampling, like the resolution of your camera? And the explanation is probably this. If you think of an arbitrary shaped stuff lying on a grid and you would count all the pixels which are partly occupied, then with a more coarse grid, you would count more pixels. Because in this case, for example, you count these 2 pixels because they are partly occupied. In this case, you count out of this pixel, if you compare, you would only count 1/4 of it. The same here, you would count these, but definitely as a grid, you would see larger sizes. And I tried to simulate these by just taking the higher resolved data, reducing the sampling by arbitrary counting together the pixels and doing the analysis again, and I really saw the shift. So the shift here is not physical, it's just due to the sampling. So you should have always in mind, this is the idea of this, that the sampling and how you create the data is strongly influencing what you measure. And then I did a first paper about the size distributions of the bright points derived from the satellite, the satellite, with this telescope, the solar optical telescope. And what you see is, first of all, it takes a long time, at least for me, because I'm not so good, to get something accepted. So practically, we sent in this work in August 2008, and it took us nearly half a year till they really published it. Because the referee is not happy, saying you should do this and that, and then the language editor is not happy, and then comes the publishing editor who says the figure needs to be scaled up or down. So it takes lots of time really to get something published. The second thing you see is that there are many co-authors, and actually sometimes it's a mystery how co-authors come, because ethically you should only put people who really put work into the paper, but actually there are other reasons why people show up. I don't know if you heard of these, the PhD comics, they are very nice. Every guy who does a PhD in physics or science, he should have a look on this comic side. It's so authentic. And you can read it yourself. So there are reasons for co-authors, like the last one, nothing to do, but he organized the money for the work, and so on. And then when you have your first real results, it's time to go to a real conference. In my case, this was the third the Science meeting. So there's a spacecraft mission, and they have science meetings dedicated to the science which came out, and they have internal meetings for the technical stuff. And they organized one in Tokyo. And if you make it that far, then you are already good, because then you made it to the conference side, which is maybe in Japan not so easy. As you can see, difficult to read. At least they have always some English explanations, and they're super fancy. So I never saw as fancy toilets than in Japan. In one case, even so, I never tried it because I didn't want it to flood my toilet. But in one case, even a public toilet, I found a toilet which had a heated toilet seat. That was kind of amazing. And you see, when you are a scientist, you travel a lot and you can learn nicely foreign languages, even for what should I say, scriptures. And the good point about going to meetings, that's why I recommend go to meetings, go to summer schools, again, networking, meeting people. So after the conference, when you listen to all the talks, all the new results, you generally go out with your colleagues and you might meet the people you work in the future together. In my case, obviously, on one evening, I was together with these two Spanish people, and he's actually, or was, well, he still is, the head of a small Spanish solar physics group in Granada at the Instituto Astrofísico de Andalucía, did I say it correctly, in Granada in Andalusia. And he is the boss there. Now he's responsible, I think, even for all space activities of Spain. And he's a lead scientist there in this group. And I met them, I found them very nice people. And when I finished my PhD, I asked him if I can join his group. And there's possibility to write applications in Austria for a grant, a mobility fellowship to go there. And he said, sure, I will support you. And I went to Granada. So if I would not have gone to the meeting, not met these people, I would not have done spectropolarimetry. This is just another day hanging out in the evening. And there in Japan, you will get lots of sake, Japanese rice wine. So I have no idea what's written here. As I said, it's funny to be in different places. And one evening that we ended up with random people. So there's kind of a drinking culture in Japan. So these were all people from some company. And I think it was Friday evening, so only me and this guy, we were scientists from the meeting, and we were just going to a pub for a final beer. And these Japanese guys, they saw us and immediately invited to us. He was, I think, the boss of the whole group. And in Japan, it's cultural tradition, it seems, Friday evening, after the work finishes in the company, to hang out together, to go out together. Because they have very hierarchical, strict system where normal employees could never complain about their boss, where they could never say what's going wrong in the work, where they could never, I don't know, say this method doesn't work, we should switch. If the boss says you apply this method, you would apply it. And so I think they invented the idea of going out together drinking. And when they are drunk, everybody can talk with the boss like if the boss would just be a friend. And so they generally get quite wasted on the weekends, especially Fridays. And they invited us, even though it was very funny because they didn't know any English. So I still remember him always only saying one phrase, welcome to Japan, welcome to Japan. But incredible evening, it was very nice. And if you ever go to Japan, another nice thing at the end of conferences is you can go with the other PhD postdoc researchers in Japan, you do karaoke evenings. So it was very good conference. And then at some point, obviously, I had to go back home. And as we talked about, he noticed so much, maybe I should introduce the mission now. So it's a mostly Japanese NASA mission with some contributions from Europe. It's a spacecraft. It was launched in autumn 2000, more than one solar cycle of data. In principle, the whole spacecraft is built around the optical telescope. So this is the tubus of the optical telescope. It's a half-meter telescope in the visible. All the optics, like the different instruments for the optical telescope, they are here in this focal plane package. Then you have here a second instrument. This is the extreme ultraviolet imager. So for the higher atmosphere of the sun. And down there you have an X-ray telescope. So practically 3 telescopes put together with solar panels flown to space. These are again the 3 instruments. And I was working with these telescopes, especially in the beginning. Here we just see the single components. Amazing for me and probably different to nighttime astrophysics is if you look at this side window. This side window is made so that the so-called heat dump mirror, which is probably drawn somewhere here, it sits, I'm not sure where it sits right now, but in principle, you have a mirror situated here. Here, it's a heat dump mirror, HDM, which is supposed to get the light of the sun out of the spacecraft, which you don't use. Because you use only wavelengths, you use only a limited field of view, like and the other light, you don't want to have it in the instrument because it leads to heating and it will decrease the quality of your images. So what they do is practically they shoot the light they don't use out of the side window. I guess this is a problem which is special to solar physics, that sometimes we have too much light, especially in wavelength bands we don't want. This is the optical setup. So the light would come from here, go to a half-meter mirror, go to a secondary, come out here. Then there's a tip tilt mirror, which is correcting for small motions of the satellite, that the image is stabilized. Go to a beam splitter, where the light is split in 3 sub-instruments. You have a probe and filter imager, which is just taking the sun through filters. Then you have a narrowband filter imager, which takes several images within a spectral line, and you have a full spectrograph. And these 2 instruments would also work spectropolarimetric, so also taking the polarization state of the light. This is how it looks integrated with the CCD cameras and the light coming in and so on. Oops. And here we see the advantage if you go to space. We said Hinode is just like a 50-centimeter telescope, so it's not too big, but it's super expensive as you fly it as a spacecraft. But this is, for example, 50-centimeter observation from the 80s from Pic du Midi Observatory, which is to go there. It's in the French Pyrenees. So the Pyrenees is the mountain range between Spain and France. And on the French side of these Pyrenees, the French built a huge observatory just on top of the mountain ridge. So it's all overbuilt, and you have several telescopes. Among them is a 2-meter nighttime telescope, but also this 50-centimeter refractor telescope, which was in the 80s like world leading, and they put like a G-band filter and observed bright points there. And this is a typical image. Now you see the change if you put your 50-centimeter telescope out of the Earth atmosphere, so away from the sea, extremely more sharp and extremely better. So you can zoom in, you see these small black dot here, which is actually a magnetic core. And now you can see it nicely. You see nicely the granules, these hot plasma bubbles rising to the surface. And you see the bright points, these small scale, highly concentrated magnetic features which are started. And now you see the effect of going to special wavelength bands. So this is just the blue continuum. Blue is often used because due to the small wavelength, it gives like the sharpest images, the highest resolved one. And CH molecule lines, and these CH molecule lines help to increase the contrast. So now you see the bright points even brighter than before in the blue continuum. And this is calcium 2H, another filter which looks not in the photosphere. So this is 2 times the photosphere, the surface of the sun. This is the next layer, the chromosphere, where the temperature already starts to increase. And you see the expansion of the magnetic fields, because you can see that these are the same features than here, but here they are already a little bit bigger in size. And this is due to the expansion of the magnetic structures with height in the solar atmosphere. And then, of course, I did more research, more stuff, more conferences. And at some point, finally, my PhD thesis was submitted and accepted. And that was, I think, April 2011. So a few more impressions. So this was during a summer school in the US. It was very nice. I can recommend it to everybody who wants to go. This was Heliophysics Summer School in Boulder, and I think it's co-financed by NASA. And if they take you, they pay the flight, they pay the hotel, and they even give you per diem money so that you can spend some money and buy food or alcohol for parties. And this was another picture of Einstein with this place is theoretically impossible in some pub. And this is again the big QMD observatory when you come up by the gondola. So there's a gondola connecting the ground side with the observatory, and it looks like a fortress with all the telescopes. Really nice. And another talk for the yearly meeting. And this is my former friend again from the summer school, but the things between us unfortunately never worked out. But still, I had a good week already, like a decade ago, with Teotihuacan, the pyramids. I think this is down from the lunar pyramid, or from the moon pyramid. If anybody was there at Teotihuacan, and this is the pyramid of the sun. And there's somewhere the magician pyramid. Who is writing all the time? That is annoying. This was me then defending my PhD in 2011. And afterwards, I was supposed to go to Japan. So it was a funny story. I think during my PhD, I applied for 2 jobs. One would have been in Japan for the Nubuyama radio telescope because it was just announced, but they never took me. And the other one was actually to work with Hinode and to work for the National Japanese Astrophysical Observatory. But they wrote me an email. They unfortunately cannot take me because they have only 1 position. I got a second email where they told me, but we have a partner institute which would be interested in you. And this was actually AISAS of JAXA. JAXA is like the Japanese NASA. And they were interested in me. And they invited me for a job interview, and they would have taken me. But unfortunately, Fukushima happened. As you know, there was this accident in the nuclear power plant in Japan. And they had a nice rocket even in front of the building. So it would have been funny to go there. But maybe I would have to wear the helmet with the Hinode satellite on top. And I was very lucky. I told you before of the Spanish guys from Granada. That's also maybe why I know a little bit of Spanish by now. And I asked them later if I can join them, and I wrote an application for a fellowship from Austria, and I got it granted. And so instead of going to Japan, which I was supposed to, I took the fellowship and I went 2 years there. They had a smaller rocket, at least in front of their building, so also still very nice. And this arbor of science growing. And there I was working a bit with the Sunrise mission, which is a 1-meter telescope flown on a balloon sphere. You want always to go up as high as possible to avoid as much of the atmosphere of Earth as possible, because it introduces seeing and blurring effects. So they flow the satellite 30 kilometers above the surface. And once it consists of 2 science instruments, as it says there. Once in a conference, I presented also this slide, I think, and I explained that they were flying it in the north, so in the Arctic from Sweden, I think, to Canada, like for 5-6 days with some Arctic circular wind, which is blowing half a year. You have wind streams which are circular, so you can observe the sun uninterrupted for several days, which is very nice. And I told this, and I showed this image, and one student asked, but if they flew the sunrise telescope in the Arctic cycle, why is there a penguin? Because in the Arctic, there are ice bears. Penguins are in the Antarctic. And I didn't know the answer, so later I asked a colleague, and he told me actually they wanted to fly it in the Antarctic, but there's lots of problems because the Antarctic is divided, as you know, in several pieces, parts of the world which belong to different countries, and you would need to get an allowance to overfly the territories, and they could not manage to go to get all these allowances because as it would be super nice, you could fly it, and it would, due to the circular wind, probably go over several orbits in the Antarctic in that sense, and you could observe the sun all the time. And so that's also why they could only do like half a circle in the Arctic now in the north, because else they would fly to Russia and they would have problems. So they crash landed it, half crash landed it with a parachute in Canada. So they let it go, I think, in Sweden, and then it was traveling till Canada. But Granada was very nice. So this is me in front of the Alhambra, which is very famous castle. Very nice history. Granada, super place to go. So I enjoyed my 2 years there a lot, and I was working a bit on spectropolarimetry there. And always good if you can get some GPM. And then I returned from Granada after my first 2 postdoc years, and I was in Graz, returning to Graz. So the first year I had money, and so I tried to raise my own project money, writing my own applications. And this is a tough job if you want to do it, and frustrating because you will be declined, very likely. So immediately when I returned in autumn, I wrote my first application and handed it in. Like I was starting in October, I handed it in December. In May, it was declined. I wrote a second application, it was declined. I rewrote the first one, and then I got it accepted. But meanwhile, I got a job, another postdoc in Leuven in Belgium. So I went to Leuven, Belgium from the short time in Austria and Graz in between. So this is our clock tower. This is the landmark in Graz. Very nice spot on a small mountainside inside the city, and you can look down. And this was the science I was then doing for a few months in Graz. The idea was to follow these post-flare loops. So flare is a huge magnetic explosion on the sun, and you build loops, magnetic loops, and they grow over time when the flare process is happening. And it practically tells you how much magnetic energy is put into the flare, so how much energy is driving away the plasma, the CME, into space. And this was then the analysis showing how these flare loops would grow over time. But actually, we never finished this work. And before I went to Leuven, I had a nice trip to a conference in Irkutsk in Siberia. I was going with a colleague from Czech Republic who knows some Russian, and he told me he always wanted to go with the Trans-Siberian Railroad, and this was our chance. And this is actually starting in Prague on the airport. And you might know, of course, that we have different time zones, but in Czech Republic, they obviously measure even the minutes in the time zones, or whatever the reason. But this was very funny, I think, that they have different minutes here pictured. Well, the red square, and if you're going to a more huge shopping place supermarket in Moscow, you find lots of runs. They have a full hallway here just of vodkas. So this is all different brands of vodkas you can choose. And this was then the Trans-Siberian, which we took from Moscow till Irkutsk, so several thousand kilometers. And somewhere in between, on a toilet in some random train station on the Trans-Siberian, I found this image, also very nice. So you see the pessimist, not the pessimist, who is too short, and the optimist, who is too large. But we students, or former students, we can do more. We can even bend space-time, it seems. And before we had the Japanese language, now we have Cyrillic. So another stuff you can learn. So this is Irkutsk. And there we visited the Siberian radio heliograph, which is a T-shaped radio heliograph. And for me, this is already more impressive than the quarter wave 1 meter antennas for the low frequency range. And here they have, I don't know, 60 or more parabolic antennas interferometrically put together to resolve the sun. And on a social day, we visited Lake Baikal. Lake Baikal is also very interesting. I think it's one of the deepest lakes in the world. And there's actually another solar telescope. So the Russians operate there, I think, a vacuum tower telescope here on the mountain. Unfortunately, we didn't visit it, but we saw it. And then I was 1 year in Leuven. Let me think, this was 2016, I think, from 15 to 16. So Leuven is a smaller city close to Brussels, kind of the capital of Europe nowadays with the European Union. And there I was involved in doing some MHD simulations of the lower solar atmosphere. So again, what we should see here is our bright point, which is the flux tube, which is expanding in the atmosphere. And here we see low-lying loops next to it. So this is actually from a model which I tried to build up. And the idea was then to shake the model and see the waves propagating in this atmosphere. But due to the 1 year, I could not really do much. Emirates with the Blue Mosque, which is very, very impressive and nice. When you visit it, then I was in India, again having fun there, and we have a third language. I guess this is just the Mr. Danger guy, so he says probably you should swim here. At least you can imagine that we did it. We tried a bit the water, but a little bit more upside of the waterfalls, not to be washed down. And then you can go with your colleagues and enjoy, for example, Goa. Bit more impressions. Then I got at some point my first invited talk during SolarNet summer school, and it happened to be in Belfast. Very nice place to go. And actually it's the place where they built the Titanic. So nowadays there's a Titanic museum if you should be around. And on another Hinode meeting, they put us to a very nice large-scale experiment. So actually, I think it was the second large-scale experiment or so. This one, I think, was close to Nagoya. It's a fusion reactor device, helical fusion device, or something like that. So you know that there's research going on for Stellarator and tokamak fusion reactors, and the Japanese are also developing one. And this is the large helical device, I think I remember. And this is the experimental hall where they build it. And the control room, very nice. And then there was a video running of the plasma shot where they try to fuse. But they also pointed out that they has a world record in something, and they're very, very proud of it. And again, it's a very funny story. I love us physicists because I think we are very cute and funny people. Because they have this huge $1 billion expensive device, but they are very proud of having the world record in the biggest sliding door, because the diffusion could be very in an emergency. They can go to these largest and heaviest sliding door in the world. And that's what they told us with total proudness. A little bit more science, and maybe I should speed up. I would have more than 10 slides left, but I'm already talking for 1 hour. So if you look at the lower solar atmosphere, we were talking before about granulation, which is put here, these plasma bubbles bringing up the new hot energy from inside the sun. Then we have strong magnetic fields like the bread points in this magnetic network. And then we have small scale fields here. These small scale fields, they form loops. The brighter and stronger magnetic fields form these large scale flux tubes going up. When you shake them, you can create waves. And you have all kinds of dynamical phenomena which we want to study nowadays. So you can see the lower solar atmosphere is kind of understood, but it's very complicated with lots of physical stuff going on, shock waves, MHD waves, weak fields, strong fields, granulations, spicules, fibrils, all kinds of stuff happens. And then there was a little bit of MHD wave stuff, which I tried to do, as I said, in Leuven. We see different types here. and these MHD waves are interesting. He put up an analytic solution for if you shake these bright points, the small scale fields, how much energy you would transport via waves in the upper atmosphere. People also try to simulate this, so they set up complicated MHD simulations to shake the flux tubes and see how the waves propagate upwards. And now I'm back in Graz since already 3 years. I'm leading my own small research project, which actually recently finished. I have my own small research group with Jose Ivan, whom you might know because he was a former student at the National University in Bogota. So this is him actually in front of the Observatorio Nacional in Bogota. So he's kind of my PhD student nowadays, and we are waiting at the moment for getting a new grant to continue. And the highlight of our last years was that we led a combined international observation campaign at Gregor, which is the largest European solar telescope with 1.5 meters. It's this telescope building actually. So this is the Gregor telescope. Here we see us in front, and our colleague from Slovakia explaining us a bit the telescope. And this is VTT, another solar telescope of which you might have heard if you do solar. So the Vacuum Tower telescope from Germany, it was one of the leading telescopes, and the FIMIS telescope, French-Italian solar telescope. And then there are various nighttime telescopes. So this is actually on Tenerife, on the Canaries. And this campaign, it involved, as I said, the Gregor telescope, but we got supported from the VTT, the second solar telescope, and from 2 satellites, IRIS Synode, and an observational telescope for full disk observation scroll. That we talked about, and this is IRIS, and these are our 2 ground-based instruments, and we had like more than 10 instruments then on the various telescopes to be coordinated. This is the observation room, very interesting, but I will go a little bit faster. What did we observe? We observed actually this active region, and there was a sunspot with which we don't want to do too much, but it looks interesting. It has these small pores, and we were interested more in these magnetic pores in the smaller one, isolated somewhere here, because it showed fine scale structure inside. Oops, 2 videos, we would see the pore in 3D, which we observed. These videos even play and the presentation doesn't crash, but I will go further. This is again the pore, but inverted, so that what is dark in the image would appear now as a mountain. So you see the 3D structure. Red colors would show you downflows, so where plasma is flowing down, and blue colors would show you upflows where plasma is coming up from the inside. And then I was also in Japan again, because it was very funny incidents. People are writing, probably they will stop. There was one night, and by accident, I met him again in Leuven, like years later in 2015. And then in 2017, 18, I visited him. As I told you before, guys, go to summer schools. Some balance. If you're now interested in doing science, there's lots of input you have to put, so expenditures. Meanwhile, it's more than 15 applications for postdocs and jobs and so on. So it's super competitive. You will get only very, very tiny fractions of what you apply for, like the fellowships, the jobs you apply for, the projects you apply. A tiny fraction, when you are lucky, will go and you will get it. But for me personally, one of my highlights is for the Synode satellite, as it was launched in 2006 in autumn. I just started to work with it. Actually, of all the people who ever finished a master or PhD degree, mine was the first master degree. You can see in 2008, lots of people finished their work with them. And for students, I would have 2 final slides. There's one slide about frustration, because I think that's a huge point in a science career, because most of the time you fight with you as a student will be experiencing first. This is that your experiment, that your simulation run doesn't work, and you have to overcome it. You have to keep going. Doesn't work. You get super frustrated. At some point, it will work. Then generally you will experience at some point that your supervisor is not of a great help, because you expect as a student, you go there, you have a supervisor, he will tell you what to do, he will tell you how to analyze the data, he will give you super intelligent hints and stuff, how to continue. But actually this is not really the case, or at least in lots of cases. And this is also, nowadays I'm coming slowly on the other side, understandable, Because if the supervisor would have done the work you do, then he would not need to do it. So you're doing something new. You do something which probably nobody before you really did or has the knowledge. So in some way, immediately when you start working, you will become the expert in it. So there is nobody really then who can supervise you. More on general stuff like getting connections, putting you to the right papers, putting you to the right algorithm. But very detailed questions can often be not answered. And then it goes on like over shitty referee boards, especially that they complain about your English. But who of us has a fluent English? We're not native speakers and so on. So you have to deal with lots of frustration. And should I do it? There was even a science article where an editor wrote about that a friend of him just finished his science career because this guy got a tenure track, but he was not able to succeed to continue afterwards. It's very difficult for way too many people who try it. So I think my personal expectation or value I calculate is that probably 100 bachelor students, or out of 100 bachelor students, maybe one will get something like a permanent position, like as a scientist or as a professor. So it's super competitive, but it's super rewarding. I mean, it's very nice. You travel the world, you have very good friends, very funny times. It's super nice. And for me, okay, these are some takeaways. And I think what's important is network, network, network. Go to summer schools, meet your friends, meet your colleagues for the future, go to conferences, get in touch with the people, build up your own network. Don't only rely on your supervisor. And of course, networking is fun and it's also important for the future. And then there's a snapshot I took in the subway in Tokyo on a meeting, which says you should not get drunk in the subway and then you should do it at home. I think one should not do it at home because drinking is more fun to do it together as a group. Normally, I would invite you to go afterwards for a beer now that we finish this talk, because I think I should finish. We spent more than the 1 hour. So thank you for listening who made it up to this slide, and I hope it was a bit of fun and you learned a bit. If there are questions, you're very welcome. The best, sorry, telescope, you mean? Wavelength. And that depends what you want to study. So if you just want to do morphologic changes like in the size, how the feature moves and so on, then the best is of course to go to short wavelengths in the visible. So you want to go to the blue continuum or a bit shorter, because then the diffraction limits are lower and you have a higher resolution. And also, if you go to these filtergram observations, maybe to 5 seconds, so you have a superb spatial and temporal resolution. If you want to analyze the magnetic field and what's going on in physical parameters like velocity in magnetic field, then you need to do spectrographic observations or also spectropolarimetric observations. So just for velocities, it's enough to get the spectrum and you can calculate Doppler velocities. If you want to do also magnetic field information, you need to go to spectropolarimetry. And then it depends what you want to do. If you want to do really detailed, very fine scale magnetic information and velocities, you should go to the infrared, because a longer wavelength gives you better magnetic field information and resolution, because the Zeeman effect is proportional to the wavelength. So a longer wavelength, like in the infrared, has a better resolution in magnetic field, but lower resolution in the diffraction. So you have some trade-offs what you need to do. But generally, it's these. You cannot go to EUV, radio, or X-ray because you cannot achieve the resolution or you're on the wrong end of the sun. So with the very short wavelengths or long one like radio, you're generally in the corona. In the corona, you cannot observe the bright points because they would not be existent anymore. As we saw before, these small scale fields, they would spread out in height and will start to merge with the neighboring features. So you cannot resolve a single bright point in the corona. Well, if you want, the physics are actually available. So you only need to know where and you could download them. So for example, the Hinode data are all public available. And if you really like to study and contribute at home, in principle, you can get all the data. For high resolution ground-based telescopes, it's a bit different. There are some data archives and it's more complicated to find them. And some data are available and others are under restrictions and only available for the people who really observe. But all the solar spacecraft data is normally totally free. So you don't even need to register. I think you have like a database search engine web page. You enter the dates and the stuff, what you want to download. You enter your email address, and a few seconds later, you get an email with a link where you can get the zip data and you can work with them at home if you like.
Okay, thank you. The next one is why is important to study the sun nowadays?
Nowadays,
Yes.
well, nowadays especially, what is one of the main driving forces, not on the small scales, but on the larger scales, is the space weather. As we have more and more technology in space, you might know that the sun, as we said before, is very active. And when these flares happen, these magnetic reconnection events on the sun, which set free a lot of energy, they tend to explode and put a lot of mass from the corona out into the space. This is called the CME, coronal mass ejection. And these CMEs travel through the space and they can hit Earth. And when they hit Earth, the nice event, what you see, aurora borealis, when the particles come down at the open field lines at the poles, hit with iron and oxygen particles in the Earth atmosphere and give the glow. The less nice part is that they can disturb the radio communication, they can lead to failures in satellites, they can also decelerate satellites because when the particles hit the Earth atmosphere, they heat up the Earth atmosphere. The atmosphere is slowly expanding a little bit, and the satellite suddenly sees more air drag because before he was in outer space. Now the atmosphere is a bit expanding. He comes into the atmosphere, he slows down, he loses energy, and in the worst case, it could fall down and hit the Earth. So what people now try to do is really understand in detail what leads to flares and CMEs and to calculate the trajectories and the likelihood that one hits the Earth, because then you could inform the satellite operators that they, for example, park the satellites in higher orbits or that they switch off the electronics that they cannot get a failure. The other point is, of course, if you have manned missions like on the space station or before on the space shuttle, then there's a risk for the astronauts because these fast particles coming from the sun, it's practically like radiation. So it causes radiation damage to the tissue. So in the worst case, you could develop cancer or get radiation ill if there's massive CME hitting the astronauts. So in the worst case, they would have to evacuate the people from the space station.
Thank you. So it's very important. The next one is uh, you have been show us very interesting pictures of you and your journeys. Do you think that exists a connection in the type of culture and their and astronomy interest?
I'm not sure about this, but I think all cultures are interested in the stars because, I mean, these fundamental questions, where are we coming from, where are we going, is present in all cultures. Maybe the difference is, but I think nowadays, at least for the educated people, most people believe in the scientific methods, in analyzing data, in getting the world picture. So maybe in some cultures you would come more up with religious solutions for explaining the universe, but I think in most cultures nowadays we all adopt the scientific methods and scientific ideas, and most cultures are interested in these. And somehow physics is very uniting in this sense because we all think in a similar way, I think.
Okay, thank you. Aliona makes a question. She says, "Have you been work with Alma data?"
No,
The
but I personally have not worked with Alma, but a very good friend of me is kind of responsible for it. Because as I said, we have good relationships to the Czech colleagues, and their astronomical institute is in Ondřejov, just south of Prague, and they tend to be the ALMA expert center for solar physics in Europe. So it seems ALMA is cooperation between Europe, Japan, and the United States, or majorly, and they have like expert centers where you can contact people who will help you with the proposal writing and analyzing the data. And in Europe, it's divided between, I think, cosmology, stellar stuff, solar stuff, and the Solar Expert Center happens to be in Czech Republic. And I have good connections, but myself, I didn't work yet with Alma. I would be interested to do something with it, but not yet.
okay, thank you. I want to search if someone.
Where you can contact people who will help you with the proposal writing, analyzing the data. And in Europe, it's divided between, I think, cosmology, stellar stuff, solar stuff, and the Solar Expert Center happens to be in Czech Republic.
Okay,
And
okay,
I
I
have good
think
connections, but myself, I didn't work yet with
that
Alma. I would be interested.
I think that was all the question. So thank you very much, Dr. Dominik, for being here. Thank you from Glark, from all the Colombian students and all the audience that are in many countries. It's a real pleasure have you been here, and that's all. Thank you very much.
Thank you a lot. Hope to see you at some point in real life. Next time when I'm in Colombia, maybe. Bye.
Hope you,
Enjoy your evening
hope
and the
you
prolonged
also.
weekend.
Thank you. Bye.